Conventional methods of risk assessment have traditionally considered two dimensions: probability and severity. Probability relates to how often the harm associated with the risk may occur. The term probability narrowly implies that risk may happen or not. It is binary in nature. We will slightly modify its standard definition to frequency, which is the number of times a risk event occurs per unit of time. This allows for a more comprehensive consideration of risky events that may happen more than once per unit of time, say a year. Severity is a measure of the impact of a risk or the possible consequences of a hazard. It is usually expressed in monetary terms. Sometimes a third dimension of risk assessment has been suggested: detectability. Detectability is the ability of a system or process controls to detect a hazardous event, a realized risk. Adding this third dimension of detectability is important based on a principle of dynamic risky environments. The longer a hazardous event exists, the greater the potential impact associated with that hazard. For example, consider a food product which may be contaminated during its manufacturing process. If the contamination can be detected early within the manufacturing process, then the risk will be substantially less than if that contamination were only detectable when it would eventually be consumed by human beings. Thus, depending on the stage of detection, the severity or impact of a risk event may vary. Now, qualitative risk analyses try to assess this multidimensional problem by naively multiplying three respective numbers for probability, severity, and now detectability. So, if a particular risk has been deemed as a 2 in probability, a 3 in severity, and a 2 in detectability, scores subjectively and ambiguously established, by the way. This qualitative method assigns a score of 12 to this risk. 12 what? Apples? Dollars? Pain units? Don't get me started on this one. This is silly and absurd and impossible to compare against other risks and/or mitigation strategies. That is why we need quantitative risk analysis. Therefore, we can analyze this three-dimensional problem using the quantitative risk analysis tool of Monte Carlo simulation. This methodology brings about lots of analytical insights that are impossible to grasp by looking at, now, 3D matrices. Let's look at an example. Step 1. Identify the risks and place them in a risk register. A risk register is simply that, a list of potential risks. At this food manufacturing company example, we have identified 5 major risks. A detailed description of each risk is added to this article. I will just mention the risk definitions: supply chain delays, third-party vendors, errors and omissions, equipment malfunction, and cyber threats. That's it. You place them on a register and you have them there. That's your risk register. Step 2. Define stages and respective probabilities for each risk. I mentioned earlier that detectability is based on the dynamic principle that, generally, the earlier you discover a risk, the less impact or probability it might have. This is the first dimension that we will define. Of course, each risk behaves differently. For simplification purposes, let's assume that we can define, for each risk, 3 different stages at which it can be detected, depending on the development life cycle of each one. At an early stage for detection, an intermediate stage of detection, and a late detection stage. We define a 4th stage at which the specific risk remains undetected for its whole life cycle. For example, stage 1 for errors and omissions risk in a manufacturing process relates to the early stages where raw materials are measured and blended. Sub-risks here might be related to measurement errors or confusion of raw materials. We might define stage 2 related to the cooking and preparation process. Sub-risks here include technical cooking errors or preparations. Stage 3 refers to the late stages of the food manufacturing process, such as packaging, storage, freezing. In this example, experts' opinion deems that the probability of detecting an error or omission is 50% during early stage 1. There is a 20% probability that it will be detected during the second intermediate stage and there is a 10% probability that it will be detected until its final stage 3. There remains a 20% probability that the error and/or omission will not be detected during its life cycle. This stage probability assignment is performed for all the remaining risks. Step 3. Define frequency and severity parameters. As in any two-dimensional model of frequency and severity, now we need to define the required parameters for the respective distribution functions. The only difference here is that we need to define parameters for each detection stage. For frequency, we use a Poisson distribution which requires a single parameter, lambda, or its mean. Regardless of the stage, we define an average frequency of times that this type of event happens per year. We use a PERT distribution to define severity. A PERT distribution requires that you provide 3 parameters: minimum, most likely, and a maximum monetary values for each risk for each stage. For example, for equipment malfunction, it is estimated that if this risk were to be detected on its early stage 1, which by the way has a probability of 60%, then its minimum monetary impact would be of $50 per event. Its most likely value would be of $200, and it would have a maximum value per event of $500. Observe that, as usually happens, the later the stage, the larger the monetary impact of the eventual risk. For an intermediate stage 2, severity would have a minimum impact of $200, a most likely value of $1,000, and a maximum value of $2,000. For a late stage 3, severity would have a minimum impact of $1,500, a most likely value of $3,000, and a maximum value of $5,000. Notice that there's an overlap of the potential impacts for each one of these stages. Finally, in this example, for equipment malfunction, if risks were to be undetected, the minimum loss would be $4,000, the most likely value of $5,000, and a maximum value of $10,000. Step 4. Create functions for simulated outcomes. To simulate at which stage the risk is detected, column S functions assign whether this will stochastically happen on stages 1, 2, or 3, or eventually go undetected according to probability table on columns B through E. Severity parameters, the minimum, the most likely, and the maximum on columns T through V, are accordingly selected depending on the simulated stage. W column integrates all 3 elements of detectability, frequency, and severity on a single convoluted scenario generated by this function. Convoluted functions are a technicality. Simply put, convolution means generating event samples of different severity values when more than one event is being generated by the frequency subfunction. It guarantees that the tails of the generated distributions are not overly exaggerated. We now declare input functions for the range x4 through AA8. These are the simulated outcomes per risk type for each one of the stages. 20 different input variables corresponding to 5 risks, each one of them evaluated at 4 different stages. We also define output variables. Total risk on cell W3 and each one of the 5 different added risks for all stages on the range W4 through W8. Once defined, the Show Inputs Outputs icon allows you to list respectively the previous declarations of them. Step 5. Run the simulation. We now define 10,000 iterations to be run with the settings icon. Once the simulation is running, Easy Risk on top of Excel will generate randomly generated values for each one of the 5 risks, assigning 4 different potential stages using respective severities. This process will repeat itself 10,000 times. Once the simulation process is finished, iteration results are stored on a data sheet, which will now contain 10,000 iterations or scenarios placed on rows for each one of the outputs and inputs previously declared. Step 6. Collect and analyze simulated statistics. After the simulation has been run, charts become available for analysis. For example, the total risk histogram shows a minimum loss of around $4,000 and a maximum of over $200,000. On average, these 5 risks accounted 3-dimensionally would amount to $55,000. However, there remains only a 5% probability that they will be larger than around $125,000. It's 95th percentile. Histograms can also be generated and analyzed for each one of the outputs which cells had been previously declared as input variables, such as, for example, errors and omissions. Moreover, statistical functions in EasyRisk allow the analysis of the collected data for inputs and outputs. For example, the EasyMean functions on columns AB through AE calculate the mean total amount for each one of the risks for each one of the stages of detectability. For example, if errors and omissions were to be detected on stage 1, they would have an average loss of $1,259. If they were to be detected on stage 2, average loss would increase 21% to around $1,500. If they were to be detected on late stage 3, their total loss would amount to approximately $1,600, a 5% increase from the previous stage. However, if errors and omissions were to slide undetected, its loss would amount to approximately $5,900, representing a 276% increase from the latest detection stage. This information can already give us clues as to how much the company should be willing to invest on detection capabilities to be able to pick up undetected errors and omissions. Up to $4,600 could be invested in such capabilities to be able to detect these potential risks at an early stage. All this information can be analyzed using a desired percentile as opposed to the mean or average. Simply select your desired statistic on the parameters sheet. On the other hand, total mean risk can be analyzed viewing a simple pie chart. On average, the largest mean risk is equipment malfunction, representing 33% at over $18,000 total. The second largest risk is supply chain delays. It amounts to over $12,000, representing 23% of total risk. Errors and omissions account for 19% of total mean risk at $10,000. Third-party vendor risks and cyber threats account each approximately $7,000, completing the remaining 25% of total risk. On the bar chart, you can easily view the gap between undetectability and the 3 previous mean losses accounted for when risk is being detected on each one of the stages. This chart also shows interesting insights. For example, equipment malfunction shows the largest mean loss mostly accounted on its undetected stage. In other words, 79% of all equipment malfunction risks arise on average when the risk remains undetected, $14,000 out of $18,000 total. If it were to be detected, this risk would be the second smallest one of the 5 types of risk. This is partially explained by the fact that equipment malfunction goes undetected 25% of the time. This fact can also be confirmed by a correlation tornado that shows that, with respect to total risk, undetected equipment malfunction appears as the input variable with the largest correlation coefficient of 0.66. A scatter plot between these 2 variables shows this strong relationship. 10,000 data points are shown on this chart. If undetected equipment malfunction were to be high, then total risk would also tend to be high. If it were to be low, total risk would also show a scenario of rather low value. We conclude, I hope it's clear that the type of insight brought upon quantitative risk analysis can never be achieved by analyzing colored risk matrices. Clear decision-making strategies become available once we're able to monetize the implications of risks occurring. It is not true you need to have hard data, that is numbers, in order to perform Monte Carlo simulation. Of course, it helps to back your decisions with historical information that supports the decision-making process. However, you can always have your subject matter experts provide 4 pieces of information required to build the model, namely the probability of detecting a risk at each one of the stages, the average frequency of events occurring per year, and the minimum, most likely, and maximum values of monetary loss of any type of risk event. Once this information has been fed into the model and the simulation is performed, the level of depth and insights achieved by quantitative risk analysis is unsurpassed by risk matrices.